shake it all about. You do the hokey pokey and you turn yourself around. That's what it's all about.
Alright, welcome to section 2.1 and congratulations, because since you're watching this video lesson right now, that means you passed the unit test for Unit 1, and that deserves a round of applause. So give yourself a big clap and maybe a pat on the back because you deserve it. We're going to talk about, this might be a little bit of a review for us again, just a little bit for this unit. Today we're going to talk about functions. This might be a throwback to Algebra 1 or even Algebra 2 for some of us. Just a heads up, I'm going to give you this little guy right here, and this little fellow means to pause the video and try the problem on your own before I actually go through it with you. I don't think there's any of these little guys today, but they might show up in the future. This symbol right here is a graphing calculator, and it is either required or recommended to complete the problem. So it might be useful for you to upload the free one if you downloaded it, or if you happen to have one of these at home with you handy, you can use it then. Alright, so let's talk about a function. A function is very much like a machine. And in other words, a machine, usually you have some type of input, whether it's rubber or leather. It goes in through a machine and you have some resulting output, like a shoe or a purse or somehow. So just like a machine changes something from leather into a shoe or fabric into a purse, a function can change a number or a value. You can put in the number 2 maybe into a function or an equation, and you're going to get out maybe something different. Okay, you're going to get an output value. Now, what is unique about a function or a machine is what comes out. So this output, okay, what comes out depends on what goes in. So in other words, I couldn't really put in a chicken, okay, into this function machine and expect to get out a pair of shoes, okay? I can put in leather and get out a pair of shoes, but I can't really expect to put a chicken in and get out a pair of shoes. So what comes out of this function, this machine, depends on what goes in, okay? And we're going to talk about input, output down here, and actually how to identify what is a function and what is not. So I'm just going to make up some random values. Maybe we'll say 25, 0, -4, -13. Okay, so just some random things right here. The idea of a function, since what comes out depends on what goes in, there's a very specific phrase, at least that I use to help me remember this, and that is one thing in, one thing out. Okay, and this is kind of why I played the hokey pokey at the beginning, because you're putting your left arm in, you're putting your left arm out, you're putting your left arm in, and you're shaking it all about. Okay, you're only ever putting in one thing, and you're only ever getting out one thing. That's the idea of a function. So if we take a look at this first table of values here, notice how when I put in -2, it's related or connected to 25. I put in -1 into the machine, I get out 0. I put in 1 and I get out -4. But notice again how I put in -2 and I am related to, or I get out -13. Okay, so in this case right here, these two numbers, notice how I'm putting in the same one value. So I'm actually putting in one thing. I know it's listed twice, but I'm putting in the same value. I'm putting in -2, but I'm getting out two different values. I'm putting one thing in, but I'm not getting one thing out. I'm actually getting out two things. So in this case, since the numbers are different for the same input value, this would be not a function. Okay, because it doesn't follow this idea of one thing in, one thing out. You put one thing into a machine, you only get one thing out. Well, we'll try the next one. Maybe all of these give out a value of 4 for some reason. Okay, so when I put in -56, I get out 4. Half gives me a 4. 0 gives me a 4. 1 gives me a 4. This is one number I'm putting in. I'm only ever getting out one number. This is a different number I'm putting in. I'm only ever getting out one number. It happens to be the same number, okay, but that's okay, because notice how I put one thing in and I only get one thing out. Same thing going on down here. None of my input values are repeated. Notice how these repeated over here, and that was not a function. So this follows the one thing in, one thing out idea of a function. So we could label it as a function. Over here, let's try another one. Maybe I'll throw in a decimal. Okay. And taking a look here, if I put in 13, I get out negative 54. 0 gives me 12, negative 38 gives me 0.2. Here's 13 again. Okay, notice how it's listed twice, just like how this one was, but there's a major difference with this one. It is listed twice, but it has the same output value. These were different. So if I put in 13, I get out negative 54. I put in 13, I get out negative 54. I kind of just have the same thing written twice. Okay, sometimes people might want to trick you. Okay, me also, just to get you thinking. But this is the same point, the same idea, just listed twice. So this is actually a function, because if I put in 13, I only get one number out. I put in 13, I get the same number out. One thing in, one thing out, we have a function. Alright, so moving on, we might come across some different names or some other names instead of input, output. If you look back for a second, these all said input, output on them, but they might say something different sometimes. Okay, instead of saying an input, it might say independent. Okay, independent. It could say domain. Hopefully these are all words we've heard before. But it could also say x, because normally the x variable we're used to seeing in math is representative of an independent domain or an input. Okay, they all mean the same thing. In terms of output, okay, you can have dependent. Instead of domain, the related word is a range, at least for the output. Instead of an x, sometimes we usually see a y. Okay, so the input-output is the main idea, but you might see these different words instead of input-output. Just a little hint, the way I remember the difference between independent and dependent, notice how this said input and this is independent. Okay, they're very similar in that sense. So the independent variable x, the domain, the input all mean the same thing. Moving on to function notation, we kind of touched base with this in the first unit. Okay, we saw this little f of x guy, and this in essence is the name of the function. So that's where we're basically going to take this part here and put it into English. The f is just the name of the function. Sometimes, or mostly, you'll see f. Sometimes we can use g or h or j or I. This can be really any variable that you want to name the function. So the f is just the name. The x is the input variable, or in other words, your domain, your independent variable, it's your input. So if you're inputting this variable into this function, it should equal your output variable, or in other words, your dependent variable, your range, your y, all mean the same thing. So you're taking this independent or input variable, you're putting it into the function, and you're getting this output variable. If we take a look down here, this is exactly what a function might look like. We have f of x equals this expression. Notice how it's in terms of x, or in terms of our input variable. Just like before, whenever we have the 2 instead of the independent variable, we want to take the place of it. So in the place of all of these x's, we're going to literally input the number 2 and solve. So 2 squared gives us 4. We have minus 2 plus 1. 4 minus 2 gives us 2, but if we add 1, we get 3. So f of 2 equals 3. For this particular function f, okay, this one we had right here, whenever you input 2, your output is 3. These numbers are specifically related to each other. On the other hand, you can actually put in an expression instead of just a number, but it's going to act the same way. In place of this x, we're going to have 2x minus 1, but we got to keep the squared. That's not really going anywhere. In the place of this x, we're going to write 2x minus 1. Just like we took the place of all the x's with the 2 over here, we're going to take all the places of the x with this expression. Also, it's really important to make sure that you put them in parentheses, because that's going to play a big time role right here. So we want to try to solve or simplify this one just like we did over here. This one's a little tricky though because this is 2x minus 1 squared, and hopefully we kind of remember that that means you have 2x minus 1 written twice. Okay, because this 2 is just telling you how many times it kind of shows up. So we want to write it twice just as a visual. And in order to multiply these two things together, we have a lot of distribution to do. We're going to take 2x times 2x, which is 4x squared, and then 2x times negative 1, which is negative 2x. And then we got to do a little bit more distribution with this negative 1. So we're going to get negative 2x, and then negative 1 times negative 1 is a positive 1. Okay, so that's a little bit of a work there to do, but I think it's going to help you to write it twice. A little clue right there for the negative or the positive 2 exponent to help you do that. The reason we need to use parentheses though in this case is to make sure that we distribute this negative, because notice how it's making the entire x negative or the entire x opposite. We need to make sure we switch every sign, and that's what's going to happen when we distribute that negative. So these signs are going to change. We're going to have a negative 2x and then a plus 1. And lastly, we have the plus 1 on the end. So you have this long expression. There's no more parentheses left, no more multiplication you got to do. So it's basically just combining like terms. We have negative 2x, and another negative 2x. So that gives me negative 6x. And then plus 1, plus 1, plus 1, which would give us a plus 3. So there's a little bit more work involved with this one to simplify it, but again, I think it's some things that we can do. On the other hand, instead of a value or an expression, maybe you're talking about a smiley face because we're all happy about math after all, right? The same thing applies. We're just replacing all of the x's with whatever is in this position. So this is really going to be smiley face squared minus smiley face. It kind of looks like ninjas, I guess. My pen's not working very well. But we have smiley face squared minus smiley face plus 1. Okay, it works the same way regardless of what's inside those parentheses. Alright, so at this point we're going to go over some calculator tricks, and we've touched base with these in Unit 1. I'm just going to show you how to do them again since we're specifically talking about this function notation. So if we bring up our calculator, hopefully I can fit it right here. Okay, and turn it on. The first thing we're going to do is actually type in this equation into the y equals button. Okay, so I think, yeah, I already did that. Okay, hopefully we know how to do that by now. And the first thing that we're going to do is use the trace option. Okay, so tracing actually involves graphing it. So let's hit the graph button, and mine shows up. Now, in order for me to have gotten this picture, I used that zoom fit option. So I hit the zoom right in the middle up top, and I scrolled all the way down to fit so that it actually or literally fits my screen. So this is a really good picture or graph of what this equation should actually look like. So once it's done graphing, we're going to use the trace option up top, and whenever you hit trace you can automatically select whatever value you want to choose. So in this case we're choosing 2, that's our independent or x value. We can hit enter, and it looks like it's 48.6. okay, so we can write 48.6 right there. Okay, that was pretty quick. Now the other thing we talked about was this table ask option. So again, looking at your calculator, if you were to hit table, okay, you got to hit the blue button first to get there. This is what your table looks like. But if you specifically want to program in a number, okay, if you want to ask the table a specific value, you got to go to this table set option. It's also in blue, so you have to hit that first. And we're going to scroll down to ask specifically for the independent variable, because that's what we're focusing on right here with the negative 3.4. Okay, so we're going to select ask, and we're going to go right back to the table option, and notice how it's blank, okay, because it's blank, the calculator is not generating this table for you anymore. You get to generate the table yourself by typing in or asking the calculator the values. So if we hit negative 3.4, okay, we're going to ask this table what it is. It gives us 72.36. Now let's say you didn't trust the calculator, okay, you're not really sure if that's correct. You could always go back to graph, and if you want to hit the trace button like we did before, you can type in negative 3.4, and we get the same answer, 72.36. So you have some different options when you're using the calculator. Some of you might like one more than the other, but I'm just trying to show you the different ways that this calculator can help you do some of these more difficult problems quicker. Alright, next one is function notation. So whenever this kind of shows up, it implies that we're inputting this independent variable in for all of our x's. So we're not really in need of the graph. Okay, I'm just going to hit clear, and it's going to go away. So I'm literally going to type in this equation with the 107 in for the x. So I have 3. I want to multiply it by 107. Okay, notice again how I'm using parentheses because I'm inputting a value. I'm going to subtract 0.2 times 107, and I'm going to add 37 on the end. Alright, so I get 34,000, I think it was 362.6. Yes, okay. So you have this option as well as actually plugging it into the equation. Don't not even have to worry about a graph. You can always do it that way. Just a little heads up, something to be careful about. Let's say you really liked this whole table ask option, and you went to your table just like how we did before with the negative 3.2. Notice again how if you hit 2, okay, you're going to get the same 48.6 as before. But check this out. The moment you hit 107, we get 34,363, but our actual answer was 34,362.6. Okay, this is the more specific or correct answer, more accurate answer, because your calculator again has only so many digits that it can hold numbers in. So notice how it's rounding. Okay, it's rounding the 6 over to the 2 to make it a 3 in this case. So just in case you do like this table option, try not to rely on it too much, because yes, you're going to get a close answer, but it might not be the most accurate. Alright, and something else you gotta be careful with. Let's say that you really liked this trace option when you were graphing it. Let's try to trace this 107. Okay, so I'm going to program in 107. And this time I get an invalid answer. Okay, now the reason you're getting that, the reason it's invalid is because take a look at the graph. Okay, it has a very specific window. And if we check out the window, remember this 107 is an x value. But notice the values of your x graph. Okay, it's only going from negative 10 to positive 10. And obviously 107 is not in between those values. So yes, it's giving you a good picture of the graph, but 107 is somewhere all the way out here on the graph. It's completely off the screen, so your calculator is not going to be able to trace it to that specific spot. Okay, your calculator can only trace with what's on your screen. So the trace option and the table ask options are very useful as long as you're using it correctly. The function notation of always just plugging it in will most likely be the best way for you to go. But just in case we're going to be talking about a lot of graphs this year, I want you to be familiar with how to use the trace and table ask options. Alright, we're probably going to breeze through this next part pretty quickly. I'm pretty sure we're used to table of values just like we did at the very beginning with input, output, or x and y. I think we remember ordered pairs always include an x, a y, and y as well, with the x coming first and then the y coming second. And just like in our function notation, okay, the independent variable is always next to the name of the function, the f, and it always equals our output value, which is normally a y. So since all of these three different representations involve an x and a y somehow, we can translate or move between all three of them pretty easily. So if you have a table of values and you know these x's and y's, you can turn the 3 and the negative 5, because notice how they're connected to each other, they're on the same level, into an ordered pair of 3, negative 5. If this is the x and this is the y, we can replace it with the x and the y, but in an ordered pair format. This is really going to come in handy when we talk about graphing, because when things are in ordered pairs, we can actually plot them as points. Now, as in function notation, if 3 is the x or independent variable, that's what's on the inside of the parentheses, so this is your input, and once you input the 3 into an equation, we don't really know what it is, but we do know we get out negative 5 as our answer, because that's our output. Same thing's going to follow with the other examples. we have an x and a y, which means we can translate that into an ordered pair, which means we can translate that into function notation. Same thing even if we have decimals, okay? We can have an x value that's a decimal with a related output, and then the same thing can go on for function notation when we're actually using the name of the function. Alright, really quickly, I'm pretty sure you're going to come across some word problems or application problems that are involving quite a bit of vocabulary or language. And I just want to take a second and help you in identifying a function from a word problem or a scenario. So whenever you see something that says depends on, that is actually, or the same as saying, is a function of. Alright, so if you see the phrase depends on or is a function of, they are interchangeable, they mean the same thing. And if something's a function, normally there's a connection or a relatedness between the two items that you're talking about. So for instance, the number of gray hairs on Konjak's head, okay, he's getting pretty old, not really, but he's getting a little bit older these days. The number of gray hairs on Konjak's head is a function of the number of students in his Algebra 1 class, because I guess they really like to act up a lot. This is the same as saying that the number of gray hairs on Konjak's head depends on the number of students in his Algebra 1 class. So in this scenario, we really have an idea about what is the independent variable and what is the dependent variable. What is the x, what is the y. So if his gray hairs depend on the number of students, then his gray hairs, maybe I'll write that up here, gray hairs is the dependent variable. It depends on it, so in other words, that's your output or your y value, which means the number of students, since that's what it depends on, is your independent variable, or in other words, your x. So you're going to come across these two phrases. It might say depends on, it might say is a function of, but they're interchangeable, okay? So we're going to take this function g, where I guess it stands for gray hairs, and s is the number of students in his class. So we want to try to figure out what do the following mean. Well, normally in this case it would say g of x equals something, okay, whatever equation or function you're talking of. So if your independent variable is always in these parentheses, this 14 is representing an independent variable, which we set up here was the number of students. So the 14 is representing how many students he has, which means if this is our output, okay, after we know how many students we have, we should be able to know how many gray hairs he has. And that's what this output value is. Gray hairs. Same thing going on over here, okay, independent variable always inside the parentheses. So we have number of students in this case, and we have gray hairs. Okay. So if he has 14 kids in class, that means he has 513 gray hairs. If he has 27 kids in class, he has 2,088 gray hairs. So there's a connection, or at least that's what they're telling us up here, there's a connection between the number of students and the amount of gray hairs he has. Alright, last but not least, we're going to talk about the vertical line test, and I think we all know, or at least have heard about this before. A graph, okay, when we're specifically talking about a picture, a graph is a function if any vertical line drawn through the graph, so completely through the graph, not just in certain places, if it's drawn through the graph and it intersects the graph no more than once. Okay, so what I did right here is I kind of have this movable vertical line. You can use your pencil, a marker, a pen, whatever you might have you're writing with. So we're going to test these different graphs here to see which ones are functions and which ones are not. So if we take a look at the first one, if I start from the left and I move to the right, notice how right now the vertical line is only ever touching the graph once. But the moment I move right here, okay, it's actually touching it twice. Somewhere right at that tip and somewhere down here. If I keep moving it, here it actually touches 3 times. One up top, one in the middle, one at the bottom. And as I move my line, hopefully not my slide, it actually ends up only touching it once again. So this one is touching the graph more than once, okay, specifically in this middle region. It has to pass once the entire way, okay, not just in certain spots, it has to work for the entire graph. So since this one fails, it actually touches more than once in the middle, this one we could say is not a function, because it fails the vertical line test. If we go on to number 2, we're going to drag it across the entire graph, and notice how it only ever touches it once. I'm going to keep moving it. It never ever touches it twice or 3 times. It only ever touches it once. So this one we could say is a function. It passes the vertical line test. Moving on to the circle, if I have it right on the edge, it only touches it once, but as I keep dragging it, okay, it actually ends up touching it twice, one at the top and the bottom, and again only once on the end. But since it fails, it actually touches twice in the middle, we would say not a function. Function. Alright, next one, we have this little square root graph, and as I drag, I notice it only ever touches it once, so we can say that's a function. Looking at this, what's called a sinusoid, it has like this repeating up and down pattern. We're going to take a look at this graph a lot in the second semester, okay? But if you drag it across your graph, vertical line only ever touches it once, so this is a function. And the last one is probably the hardest, okay? Notice how the graph is in pieces. It's called a piecewise function. And as I drag the graph across, okay, it only ever touches it once, okay, down here on this part. But then right here, okay, right there, it's really hard to tell if it's a function or not because to us, it looks like it's touching it twice. Somewhere on the black dot and somewhere on that open dot, okay? But hopefully we remember that closed dots mean that the value exists, whereas open dots, the value does not exist, or it does not equal that value. So this vertical line, when it's on top of those, it's actually only touching the closed dot. It's not touching the open one because that point does not exist. So even though it looks like it's touching twice, it's only ever touching once. Okay, but as we move on, it's only ever touching this horizontal line once until I get right there. Okay, so this is where we have a problem because I have a closed dot, which means my vertical line is touching it, but I also still have this horizontal graph up top as well, and it's touching it too. So right there, it's touching it twice, which means it's not a function. So it looks like it should work because we have these open and closed dots almost on top of each other, but there's just this little section right in here where it's touching it twice. And if it happens at all, it's not a function. Alright, so I think that's it for the first section of Chapter 2. Good luck on the practice and the application and the mastery check, and I'll see you guys later.